Good morning, everyone. This the eighth training day for Lebanon. Today we are going to describe or illustrate the procedure for determination of soil moisture content. Soil moisture is very important uh, very important characteristic of the soil because the availability of water in soil is very essential for growing of vegetation, and in natural landscapes the vegetation will suit it to soil type, the climate, and also the soil moisture regime. And this is very obvious that each country or each ecological zone has its characteristic vegetation cover. For instance, for Lebanon, for example, they normally grow citrus crop, olive, and others. While in the others arid land and tropical ones, you can find other types of vegetations, tropical fruit, for example, mango, bananas, and etc. Uh, Also, the soil moisture regime, it concern about the way in which moisture content varies within and between years, and even within the year itself there will be some variation of soil moisture regime due to the fluctuation of uh, water movement, and also as results of variation in rainfall. So normally during the autumn, the soil moisture is high within the soil profile, while in the during the non-rainy months, the water or soil moisture drop very drastically. Of course, when the soil moisture fall below the wilting point, the plant will going to struggle to survive and even will show some symptoms of wilting. And if this condition continue for a long time, maybe this lead to the death of the plant. On the other hand, when the soil is waterlogged or the moisture is too much, this will also lead to unavailability uh, of oxygen and air in general, and this of course will lead to the death of crops and plant in general. So the availability of water is a major factor that controlling the biogeography of plant species. Also, the importance of soil moisture, it work as a storage system that regulates the passage of water from rainfall arriving at the land surface to its return to the sea. If there is no soil or there is no storage of water, the runoff will be very high. So most of the water that come from the rainfall will go to the sea or the lakes. But the soil work as a storage system. And this storage means that some river continue to flow long after rain has stopped falling, and perhaps for months or even years. So this is related to the hydrological cycle, or related to the hydrological system, that the soil play a hydrological role. Also, soil moisture can act as a short circuit for water pathway direct to return to the atmosphere by evaporation and evapotranspiration. That the storage moisture in the soil, by at the end it will be absorbed by the plant, and then as you know, the plant conducted process of evapotranspiration, and this the water come evaporated to the atmosphere, and this help retain the moisture can itself affect the local weather. And it is very this one is very noticed. The areas with good vegetation cover normally they have a very good weather, and for this reason most of the people encourage to plant trees and others to make the weather at their areas in a good way, which is normally between bracket called microclimate. Soil are essential for the soil moisture also is essential for conversion of plant material into soil nutrient required by other soil organisms and plant. As you know that the nutrient itself cannot be available to the plant unless it's dissolved in water. So here the water as the great dissolving material is very important to increase the availability of nutrient for the plant. The principle behind calculation of soil moisture content is it is very simple and very straightforward methodology that the gravimetric water content determined by drying wet soil in an oven at temperature 105. So you just take the weight of wet soil, then subtracted by the weight of dry soil, and the difference will give you the gravimetric water content of the soil. Then after dividing this by the dry weight, you can get the soil moisture content. Why we use oven dry? Because at temperature 105 degrees centigrade, because the hygroscopic water cannot be removed unless it's subjected to this temperature. Normally in the water, the soil system consists basically of 3 phases: the solid phase, the water phase, and the gaseous phase. So the liquid phase, there is 2 types of water. That water, free one, that within the pores, between the pores, there will be water, and also around the soil particle. Around the soil particle, it make a thin wall around the soil particle, and this type of water is called hygroscopic water. And this hygroscopic water cannot be removed unless the soil is dried at temperature 105 degrees centigrade. The apparatus, they are very common one, and in most laboratories they are available. You just need electric oven, thermostat, desiccator, and of course a balance, precise balance. The sample, it is also the normal one, 2 millimeter sieved air dry soil. The procedure: you weigh 5 grams of air dry soil into a previously dried and weighted weighing dish with the lid, a labeled aluminum dish. Normally, this dish one is always made of metal, aluminium, or in other places iron. because you will going to put it in an oven. Then dry in an oven at 105 degrees centigrade with unfitted lid overnight. Then remove from oven, fit lid, cool in a desiccator for at least 30 minutes and reweigh. All weighing should be recorded to 3 decimal places. Transfer a representative subsample of the soil to a third can with lead for accuracy. It is where possible to use at least a 25-gram sample. Weigh dry to constant weight at 105 degrees centigrade and weigh again. The calculation, the moisture percent of moisture content equal wet soil in gram minus oven dry soil in grams over oven dry soil in gram multiplied by 10. And the result should be recorded to 3 decimal places. This is a methodology, and I try to, from the request of yesterday, I prepared the video of the internet.
This video will cover the process of water content determination for a given soil sample. At
You
first,
see it, yeah?
we take an accurate balance, tear it into zero reading.
Yes, we can see the video.
Make sure that the can is clean and dry. We level it properly and measure the weight of it. We take some sample from the given soil sample, put it in the container, and again weigh the can with the moist soil. For this sample, we need to take a minimum of 20 grams of soil since the maximum particle size was smaller than 4.75 millimeters. Keep the container in the oven for 24 hours, allowing the water within the soil to evaporate. Set the temperature of the oven between 105 to 110 degrees Celsius. After 24 hours, the soil will be completely dry. We take out the container carefully. Record the final constant weight of the container with dried soil sample. A sample calculation is shown here. The weight of the can with moist soil and weight of the can with the dry soil have been recorded. So the moisture content can be determined from this formula, dividing the moisture in the soil by the dry unit weight of the soil. Thus, the moisture content of the soil can be determined with oven dry procedure.
So, floor is yours. I think it is very simple procedure. Floor is yours. for any comment, discussion as usual.
Thank you, Doctor.
No, thank you, doctor.
No comment.
No
Very
comment.
clear.
No, we actually, when RAB sent us samples for to measure the density for to Fanar and to Tal Amara, we do this procedure.
Yes.
Yes, we have the soil, the wet soil, and then we put it at the 105 degree overnight, then to cool it down, and we wait the dry soil.
Mhm.
But we don't do the calculation because he knows the volume of the cylinder. He took the sample to do the density. We only give him the weight of the soil.
Yeah.
And after drying and
We sieve the
grinding,
sample.
grinding is we sieve the samples for gravel and fine particles.
Yes.
So this for calculation of the density.
Mhm. Also, I think that it is very important that to know the moisture content, because most of the calculation or even the
The organic matter needs the
organic
moisture content
matter.
factor.
Yes, and
Mm.
if you want to transfer also the concentration from mill equivalent to percent, in all these cases you need to have an oven dry base soil.
Mm.
So it is a first step in soil analysis to have the value of the moisture content in the soil for most of the others soil analysis, because most of them they are calculated based on over dry base.
In
If you go
summer,
to the percent, for instance.
in summer when the soil is dry,
Mhm.
we don't need to do the moisture content of it because it's already dried. Of course,
but
it's at 105 degrees, but we can put that the factor of the moisture is 1, for example. Can't we do that?
No, even
No?
even
Okay.
during the summer, even during the summer, there is still part of water that is attached to the soil,
The
especially
hygroscopic one.
the hygroscopic one. This
Okay.
hygroscopic one cannot be removed by the air dry or
Mhm.
and also this methodology during the video, somehow it is very you can say it as a robust, but for accuracy you have to take the reading within and put the soil indicator, because even from oven to balance,
Yes.
the water will gain again. It is hygroscopic water.
From
You know
from the
hygroscopic
air
water is,
humidity.
yes,
Yes,
from
yes.
yes.
But if we don't have a desiccator, can we leave it in the oven to cool down with shutting off the oven? That's what I do.
Yes, so I do. So I.
Because we don't have a desiccator, we leave the samples in the oven, but it's turned off till it cooled down by itself.
Yes, yes.
We can do this.
Yes,
Okay.
but the best way is the best
To
way
put it
is
in the
to have-
desiccator.
yes.
بدنا نطلب
Have a little
desiccator مريض.
desiccator. ما بيسرع كل العينات إذا كان
Yes,
عندنا.
yes. We usually have like 40 samples.
Yes. For the density, كانوا عم بيجيبوا لنا 3 samples from each. 3 samples from each place.
Mm-hmm.
It's like a
sub-samples.
triplicate. It's a triplicate.
Triplicate.
So we don't have.
In case of replicate, normally if you for replicate, if you take for one, then it can be represent for the other two.
No.
But,
no, we do the 3 samples. We cannot make one and.
It is replicate for the same subsampling, or it is replicate
3
by
subsamples. كان عم بجيب لنا 3 سب سامبلز للدنسيتي يعني، بس المفروض انه الفوليوم سيم فوليوم فور ذا 3 يعني، لانه عم ياخذهم من زيت المطرح.
Hey, but we are not sure about this.
Yes.
Yeah, if you are sure, then it is.
No.
In your
no,
case, it is not. Yeah, it is. Each one is a unique sample.
They don't tell us if it's the same. If it's the same soil and the triplicates. Maybe it's like a, I don't know, a test for us to see if we are doing a good job or not. I don't know. Where
you're doing a great job. You're
I'm
doing a
sure.
great job. You are doing a great job. I know. Yeah. But the secators, they are not expensive in general. It is glass. Okay.
Okay.
So we can move to the particle density, yeah? Particle and bulk density. Valeria, if we can start with your or
What? I didn't hear you well.
we can move to the bulk and particle density.
Instead of the bulk density, it's like you want.
Okay.
Today I think that we have a very quick and rapid methods in general. So the second presentation, I combine it because bulk density and particle density, they are very I think they are very not correlated, but they are very they have a very relative impact or important on the soil. So both of them, they are density. So what we mean by density, normally density represent weight, mass per unit volume of a substance. And of course, the density is measured for solid and liquid substances. So in general, density equal mass over volume. And the soil density is expressed in two well accepted concepts, that namely particle density and bulk density. We started with the bulk density. Highlight more in the bulk density in the next, or actually in the late presentation, we will go into the particle density. So what we mean by bulk density? Bulk density is an indicator of soil compaction, and it is calculated as the dry weight, often dry weight of the soil divided by its volume. And this volume, in case of bulk density, includes the volume of soil particles, the solid part, and the volume of pores among soil particles. And bulk density is typically expressed in gram per cubic centimeter. So in general, the bulk density is we concerning about determination of weight of the soil, and then go to the determination of volume. So then after determination of weight and volume, it is very easy to have the bulk density of the soil. So the important thing that within the bulk density, you are taking the volume of solid and the pores volume. So for the bulk density, the open dry weight of a unit volume of soil inclusive of pore space is called bulk density. And as a general rule, or the very common one, that the bulk density of the soil is always smaller than its particle density. Bulk density normally decrease as a mineral soil become finer in textures. So the soil with the sandy soils, their bulk density is its bulk density is higher than the clay soil. The bulk density varied indirectly with the total spore space present in the soil and give a good estimate of porosity of the soil. Normally soil with high bulk density, this indicates that this soil has more pores within it. And for agriculture, from agriculture point of view, bulk density is of greater importance than particle density in understanding the physical behavior of the soil. And normally when we talk about physical behaviors, that the compaction, the movement of water, and also availability of air. So all these factors, all these parameters, they are directly influenced by the bulk density. Generally, soil with low bulk density have favorable physical condition. In the principle, the critical value of bulk density for restricting root growth varies with soil types, but in general, bulk density is greater than 1.6 over centimeter 10 to restrict root growth. Yeah, this means that when the bulk density is high, the volume is low, there is no pores, there is no enough pores. So this, of course, will hinder or prevent root to grow, and of course, this will provide poor physical condition. Sandy soils usually have higher bulk densities, ranging from 1.3 to 1.7 gram per cubic centimeter than fine silt, and clay one range from 1.1 to 1.6 gram per cubic centimeter, because they have larger but fewer pore spaces. In clay soils with a good soil structure, there is a greater amount of pore space between the particle, although they are very small, and many small pore spaces fit between them. Soil rich in organic matter, example peaty soils, can have densities of less than 0.5 gram. And this the reason that yesterday I think Abir mentioned the issue of addition of organic matter to the soils to improve or to reclaim a saline soils. I respond for that the organic matter itself is not have to do with the salinity, but it will improve the soil physical condition, and this will improve the possibility of leaching of salt from the root zone. For the apparatus, balance, drying oven, moisture boxes, and core sampler. And the core sampler can be anything from an elaborate power driving machine to a short section of thin-walled brass tubing with an internal closely fitting ring of clock spring soldered in place to form the cutting lid. The sample here is just moist core soil sample, and this methodology is basically can be done or the soil preparation here start from the field. The procedure, it depends on the type of core sampling and soil condition. If the soil is wet or it is dry, what the core sampler type we use. But usually a flat soil surface, either horizontal or vertical, is prepared at the desired depth. And normally for the bulk density, it should be taken for each depth, because some soil layers can have a good bulk density, while the others maybe they have a higher bulk density. And this depend on the layering of the soil profile, as we discussed, I think, yesterday. And the core sampler is pressed or driven into the soil. The care should be taken to see that no compaction occurs. It is very important to take care of the pressure you pressed on the core so that you cannot make artificial compaction or make some disturbance of the soil sample during the process, so that a known volume of soil having field structure is obtained. The oven dry weight of the sample is then determined. So by in the bulk density, gram per centimeter, cubic centimeter, you have the weight of oven dry soil minus weight of the soil minus weight of oven dry soil over volume of the soil. I think I make here. I need to change this. Anyway, I make some typographic mistake, but in general you have the weight of
wet soil.
Yeah, weight of the wet soil minus
weight of oven dry soil.
Yeah, over volume of the soil. We continue with the particle density, or we can wait here a moment to discuss this? What do you think?
Doctor, I think there is a problem with the equation.
Yes.
Not so the oven dry over the volume. We have to remove the wet. Okay.
Okay. Weight of oven dry. It is not a minus. It is just weight of oven. Yeah. Thank you, Maria. I put this as a oven dry soil. Weight of oven dry soil over volume of the soil. Do you want to discuss little about bulk density before we go to the particle density, or we finish them both and then we can discuss? What do you prefer?
For me, continue and then we discuss later. I don't know.
For others, they are agree on that. Are you agree on?
Yeah, no problem for me.
Yes.
That. So with the particle density here also we concern about density, mass over volume. But here's the weight per unit volume of the solid portion of the soil. not all the system, that the solid plus gaseous and spores. Generally, particle density of normal soil is 2.6 gram per cubic centimeter. The particle density is higher if large amount of heavy minerals such as magnetite, limonite, and hematite are present in the soil. So in general, the mineral soils have high particle density in comparison with organic soils or in others. Increase in organic matter of the soil decrease the particle density as well. In a metric system, particle density can be expressed in terms of megagram per cubic meter. Thus, if 1 cubic meter of soil solid weight 2.6 megagram, the particle density is 2.6 megagram per cubic meter, since 1 megagram equal 1 million gram, and 1 meter equal cubic meter equal 1 million cubic centimeter. Thus, also, as we mentioned, that the particle density can also be expressed as 2.6 gram per cubic centimeters. For the apparatus balance, vacuum desiccator, and picnometers. And for particle density, the most accepted methodology and standard one is picnometer methods. So for the procedure, you weigh a picnometer when filled with air. You just weigh the picnometer, air dried picnometer, oven dried picnometer, without addition of anything, and this is WA. Then weigh picnometer when filled with water, and this WW. Weigh picnometer when partially filled with an oven dry sample of soil, WS, and then you fill the picnometer with water and soil. So weigh picnometer when completely filled with soil and water, and this is WSW. To exclude air, picnometer contain the soil with enough water to cover should be subjected to a several pressure reduction in a vacuum desiccator, and then allowed to stand for a number of hours under reduced pressure before completely filled with water for weighing WSW. The calculation, the particle density dB of the soil in gram per cubic centimeter is then given by the formula density of water multiplied by weight of picnometer with soil minus weight of picnometer filled only with air, and all this divided by weight of picnometer when filled with water plus picnometer filled with soil. All this minus weight of picnometer filled with air only minus weight of picnometer filled with soil and water. Finally, as I said, that the particle density and bulk density together as a parameter can have their influence on the porosity. So the porosity of the soil identify or indicate the porosity is the fraction of soil space not occupied by soil particle. totally occupied by air, and of course when there is water, this part of porosity is filled with water. So the porosity identifies a space for water and for air. The porosity may be calculated based on this formula. It equal to particle density minus bulk density and divided by particle density. So from the particle density and bulk density, you can determine or measure the porosity. And porosity is, of course, it is very important physical properties because it indicates the physical soil condition, and of course this have a great influence on availability of water and also availability of air. So with high porosity, you have enough space for water and air. But if the porosity is very low, this means that there will be very low space or very little space for water and air. Um, so is picnometer. There are many videos showing that how the picnometer is work. I can share it with you, but firstly we have to make, if there is some intervention from your side, then we can try to see these videos. It will be helpful in process of understanding of this two methodology. So all in all, I think we can conclude that the difficult part in determination of bulk density or particle density is how to know the volume. The weight of the soil, oven dry soil, is very easy. You just take the soil and put it in oven dry, then you will weight it, or for in case of bulk density, you just take the weight of soil. But these methodologies try to find a ways to determine the volume. So the whole procedure seek or looking for a way to determine the volume. So here the process is concentrated on this issue. The weight of the mass can be determined very easily, but how to determine the volume, this is the story of these methodologies. The floors is yours now, and we can discuss a little about this. The good news that Clary prepares something, what we described yesterday about the rapid methodology of determining particle density. She will share it with us also, but also I tried to prepare some videos so that the two methodologies will be very clear for you. The floor is yours.
We start with the particle density, or we want to start with the bulk one, with the questions. Okay, I will share my screen. Can you hear me?
Yes.
Okay.
Yes, yes, yes.
Okay. Okay. Can you see the slide?
Yes.
Okay, good. So I did like you told me yesterday. I filled the cylinder with the 60 milliliter of distilled water and weighted 10 gram of air-dried soil. Then I pour it into the cylinder and I measured the volume of distilled water that was displayed by the soil solid. It's like almost 5 milliliter. And then for the calculus, we make the weight 10.01 over the 5 milliliter, which is equal to 5 centimeter per cube. That's the method. Maybe we can use it if we don't have the picnometer.
Yes. So the particle density is equal to
2.002.
okay, 2.002.
I guess. Yes.
And the soil is seem like sandy soil.
This one, yes,
Yes.
yes.
And this is a very rapid method to
Yes.
determine the volume. And here we depend on the rule of displacement of liquid. Yeah.
Yes. Can we use it without using the water? We can take a mass of soil and put it in the cylinder, and we can check.
Yes.
We can do this
And
without water?
no.
No?
Actually, you're looking for the volume. You're looking for the volume of the soil. So when you put the soil on water, the water will fill the pores. So there will be no space. So just the soil. So the increase or increment in volume here is attributed to the soil, solid part without any pores. And you know this belong to this displacement law, Archimedes. That if you put the water displaced or the volume of water displaced is equal to the weight of the subject. So here, what you have, this increment in volume in the measuring cylinder is attributed directly to the volume of the soil.
I have a question here. We can use the air-dried soil, not the oven-dried soil. Or
Such
no?
cases. But what's the weight? About the weight, you have to use the oven dry.
Oh, we have to use the oven-dried.
Yes.
Okay.
Yes.
I did this with the air-dried soil because
Yes.
I cannot put it in the oven overnight. It should be overnight, right? At 105. Yes.
Yeah. Yes.
Okay, so we have to fix it.
Anyway, this methodology at least will give
We
some
have to fix it. Oven
dried.
dried.
Yes.
Okay.
Of course, because you said yesterday that you
I don't have electricity at night.
yesterday I remember that you mentioned somehow that you don't use to measure particle density and bulk
Yes.
density.
No, we don't
So at
measure
least
soil moisture, nor bulk density, nor particle density.
so at least this methodology we use here in the laboratory to give some an idea.
Yes.
Yeah, of course the accuracy is not high, but at least it will give you some measurement related to the particle density when it is needed. And it is very fast and easy in general.
Yes, no need for chemicals to be used.
بس سؤال ليه حاطين 60 ملي الفوليوم؟ هو هيك ستاندر ولا انه في سبب؟
يعني ما 60 ملي ما رقم، بس رقم ممكن يكون لو في زيادة. اي ليفت مثلا 40 ملي، يعني خلينا 40 ملي على اساس نشوف، يعني حتى لو في زيادة ما بتكون اكتر من كده، يعني بتتيح فرصة انك، لكن ممكن تكون 50، ممكن تكون 70، يعني ما بس رقم ما عنده هنا، يعني ما بتملى المجري سلندر فل لحد ال 100 ملي، انما بتترك مساحه من المجري سلندر للزياده اللي بتحدث نتيجه لاضافه الصوت. دي الفكره يعني.
هي تكون 50 مثلا ما بيأثر.
ممكن.
We can use here the tap water also instead of the distilled water.
In such case, it is better to be distilled water because you know that always with the density, the density of water, tap water is its density is very varied. But in general, there is some assumption that the particle density of water is 1 centimeter per cubic.
Yes.
Yeah, the density of water is 1.
Is 1, yes, for the distilled. Yes.
Okay, previously we showed you how to drive the ring and clear the residue, and
I will share with you a video to determine bulk density.
Okay.
So now I'm going to show you how to go ahead and remove that ring, and we do need to be a little bit careful. The other thing is to make sure, because we're measuring unit of volume, or weight per unit of volume. So I want to make sure that I've driven it evenly, so I'm right at 2 inches all the way around the edge, so my ring isn't crooked. And then we're simply, to do this, we're going to go ahead and have to excavate around the ring. And what we want to do is try to keep all the soil in that volume, which is 3 inches of depth for this particular and it's a 3-inch diameter. We're going to go ahead and excavate it. Now that we've excavated around the edge of the ring, I'm going to make sure to get my trowel. Some cases I've seen people use a tile spade as well underneath the ring. We don't want to lose any soil. Okay. So when we do this, we also need to be careful that we cover the top so we don't lose any soil from the top. Okay. Okay. And then so we have the exact amount we need. We have in your bucket, or you can get this out of your kitchen drawer, a knife. And we want to go even to the bottom of the ring. That. Okay. So we're going to go ahead and make sure to have something underneath the bottom so I don't lose any of my soil. And I pick up a clean Ziploc bag. Go ahead and we're going to put the soil again into the bag. So the importance here is that we get the exact volume of soil. So if we lose some of the soil, we may have to redo this. So we want to be pretty close to exact to that 3-inch mark, as well as the diameter of the ring. Then I can use the knife to go ahead and make sure all the soil cleans out. Some cases you might use the same ring you use for infiltration. So now I went ahead and got everything in the Ziploc bag. I go ahead and close it, and you want to label it. In this case, this is the compacted row or wheel traffic row. And then you go to the next part of the field and collect it as well, and we're ready to go to the lab. Now we just got back from the field, and we have our sample that we pulled from the bag. And we have Virginia Jen with ARS, research soil scientist, is going to help us through step 6 through 11 and in the guide. So the first thing we're going to do is go ahead and weigh our sample bag and record its weight in table 2 with the soil in. The next step is to go ahead and weigh an identical clean empty bag and record that in table 2. Next step is to go ahead and weigh an empty microwavable. In this case, we're using a tray. If you have a cup, something that's microwave safe, and then record its weight in table 2. Okay. And then the next step is to go ahead and take our sample bag. We're going to mix the sample thoroughly by kneading it with your fingers. You know, Virginia's done this quite a bit. And then we're going to take our 1/8 ounce level scoop of the loose soil that's not packed down, but struck off level at the top. Okay, and then place it in the tray. So we're going to go ahead and weigh that moist subsample before drying it. Okay. So now, and then record that. Now we're ready to go ahead and place the tray with the soil in the microwave. We're going to place the tray containing the subsample, and we're going to dry it for at least 2 4-minute cycles at medium power. Now we went through our first 4-minute cycle. We're going to go ahead and weigh the subsample. Okay. Now, after our first cycle, we're going to go ahead and record that on some notes, and we're going to go ahead and dry it through 1 more 4-minute cycle. Okay, now we just got through our second 4-minute drying cycle at medium power. We're going to weigh it, compare it. In this case, we changed moisture just a little bit, so we're going to have to go through a 3rd cycle. Okay, we've just completed our 3rd drying cycle. We're going to compare it to the weight that we recorded from our 2nd cycle. In this case, it's weighing exactly the same at 153 grams. So we're going to go ahead and record that weight in table 2 in column F. Okay, now that we've got a dry weight of the soil plus the tray, we're going to go ahead and finish our calculations following the example. In this case, we go ahead and go through the example. We're going to take the dry weight of the soil minus the weight of the moist soil minus the dry weight of the soil divided by the dry weight, and that gives us the grams of water per gram of soil. And then we run through the bulk density calculations, basically all the way through to where you determine the grams per cubic centimeter squared. Once we've done that, completed those calculations, we're going to go on to table 3, and we're going to use the same information that we recorded off of table 2 or determined. We're going to determine soil water content. So we take the soil water content by weight from table 2 in grams per gram. We take the bulk density we recorded, which is 1.2 grams per cubic centimeters, and then determine using the formula, the volumetric water content. And then from that, we take the volumetric water content times 12 inches of soil depth, so we can get the soil water content in inches per foot. After that step, table 3, we're going to go on to table 4 and determine soil porosity. And again, soil porosity, we talked about that earlier. So we take the grams per cubic centimeter, the bulk density. We run through the calculation of 1 minus soil bulk density divided by 2.65, which is the density of rock. And then we get a soil porosity. In this example, it's 54.7% pore space, which is pretty good. Ideal soil would have 50% or more pore space. Next, we're going to determine soil water filled pore space, and taking the volumetric water from that we determined from table 3, and then the soil porosity that we determined from table 4 in decimal 0.547 in your example, determines volumetric water content, which is divided by soil porosity times 100 to give us a soil water filled pore space. So from that, you've determined quite a few things: so porosity, soil water content, soil water filled pore space, determine if we've got an ideal situation for microbial activity, bulk density determination. We would compare that back to the ideal bulk density that you'd have for your soil texture. And also in the table, it lists if you have a bulk density, at what level would it impact root growth. So you want to do that with your students and drive home the importance of bulk density tied to compaction, tied to all the important soil functions and processes that occur.
So
دكتور، في بالبروجرامات لما نعمل عليهم التكستشر بس نحط البرسنتج للبارتيكلز بيعطينا بالك دنسيتي، فلأي مدى فينا نقبلها تكون مقبولة أو كتير بعيدة عن الواقع؟
والله هو البارتيكل دنسيتي طبعا بيعتمد على السويل تكشر، فلو في كاليبريشن ميثود ممكن الى حد كبير تدي مؤشر، لكن طبعا دايما الامبيريكال ايكويشنز مفيده، لكن الميجرمنت الدايركت مرات بتكون ادق، لكن فعلا يعني هي بتدي مؤشر
لا ما عم شوف اذا مقبوله يعني او لا، بس بعرف اكيد
لا
الشغل
هي مقبوله طبعا، مقبوله
أوكي.
بتدي امبيريكال، ما هي مقبوله. لا لو لاحظت في البرزنتيشن انه البارتيكل دنسيتي واحده من العوامل المؤثره عليها بشكل اساسي السوليد بارت، المينرالز كومبوزيشن اوف سويل، هو ده على طول بيظهر في السويل تكشر.
اوكي.
لكن الميثود سهله، يعني هم طبعا عملوا اكثر من وزن باستخدام مايكروويف، لكن انت لو قدرت تحصل على المويستشر كونتنت كان ممكن وانس ان اول تاخد قرايه اوبن دراي ويت وتطلع النسبه بتاعت المويستشر كونتنت تقسيمه من الوزن بتاع التربه اللي هو جابه من الحقل. بالتالي
عينات دكتور صغير هيك عملناهم، اخذنا كل الوزن اللي جايبه، يعني كل اللي بالكيس نحطه بالفرن، يعني ما شلنا سب سامبلز منهم مثل ما هن.
ممكن عندي تكون يعني اسهل
انه بارت واحده ليش نقسمهم؟
ايوه هم بيوزن مره ومرتين وثلاثه
20 هيدا 48 hours بالاوفر.
ايه 48 hours كنا نتركهم.
كان ممكن يتركها 24 hours وياخد القرايه بتاعت المويستشر يقسمها ويحط على الاوفن دراي ويت يعني. لكن البولك دنسيتي هنا بهذه الطريقه سهله يعني، او بمعنى صح يعني هي حقليه اكثر. في طريقه اسمها الكلود ميثود. الكلود ميثود ديك لابوراتوري ميثود. اللي هي الكلود بتاخد كتلة كتلة من التربة، كتلة دائما للتربة اللي فيها كتلة، يعني ما مفتتة، ودي غالبا تكون نفس تربكم، يعني ما انتوا الترب بتاعتكم ما سانترو، ما بتكون مفتتة، بتكون عندها ستراكشر، بتكون عندها كتلة. فقبل ما يحصل لها جريندين، قبل ما تطحن، بتاخدي كتلة من التربة، بتعملي لها كوتين بمادة تمنع انه المويه ما تدخل. هي ممكن يكون واكس، شمع، بروفاين، وكس بروفاين، بيكون محلول. بتعملي ميرسين، بتعملي غمر للكتلة بالشمع، بتوزنيها، فده بيديك تربة، كتلة من التربة ما ممكن يحدث لها شنو بالهواء الموجود بها، بالفراغات. مع ذاك هنا الحجم ممكن بالإزاحة، برضو ممكن تجيبي إناء بتاع إزاحة، تدخل الكتلة معاها الشمع، كمية الموية اللي بتنزاح هي دي بتكون بتساوي حجم كتلة التربة زائد الشمع المحيط بها. داك بتتخلص من الحجم اللي ممكن يكون راجع لشنو للشمع، وبعد ذاك عندك الوزن اصلا موجود، بيبقى الوزن على الحجم. فطريقة الكلود ميثود دي برضو طريقة للبلك دنسيتي، طريقة شنو يعني برضو طريقة أخرى برضو معتمدة. يعني ممكن ارسل لكم الماده بتاعتها، اللينك بتاعتها، لو شعرتوا انه برضه ممكن تعملوها، بس هي بتحتاج وزن لكتله التربه في الماء وفي الهواء. عندكم الموازين اللي بتربط عليها حبل، يعني ممكن تربط عليها خيط، بعد ذاك توزن وانت تحت المويه، ما زي الميزان البلص ده، الموازين القديمة، يعني كلود ميثود دي. طيب في ممكن نحاول برضو نشوف كان البيكنوميتر للبارتيكل دنسيتي. particle density أنا I will share برضو with you لأنه
The density of a substance is defined as the mass per unit volume. Water has a density of about 1 gram per cubic centimeter. If an object has a greater density than water, then the object will sink in water. However, if the object has a lower density than water, the object will float. Today, we will see how to find the density of an irregular solid through the water displacement method. Here, we have a stone and a measuring jar filled with water. We have taken 1000 milliliters of water here. Weigh the stone. It weighs 520 grams. Now put the stone in water. The water level rises to 1220 milliliters. So the volume of the stone is new water level minus original water level. That is 1220 minus 1000 gives 220 milliliters. The mass of the stone is 520 grams and density is mass upon volume. Density of the stone hence is 520 by 220, which is 2.36 grams per milliliter. Since 1 milliliter is equal to 1 cc, density of the stone can be expressed as 2.36 grams per cc. The density of a substance is defined as the mass per unit volume. Now that you know how to find the density of materials that sink in water, can you find out a way to measure density of materials that float?
Any comment?
Everything was clear. No,
No
really.
لا لا فعلا هو الليلة عارف إنه الموضوع بسيط يعني ما أنا داير أحاول أمس كان في بيكنوميتر لأنه البيكنوميتر برضو I will share with you برضو عن البيكنوميتر. Very nice video. Yeah?
Yes, but this one is for the particle density, right?
Yes.
Yes, and with the probe density of probe, it's also for the particle one, not for the bulk density.
Not for the bulk. Bicnometer for particle density.
Yes, but in the last 10 seconds, they showed us like a probe that can measure the density. It's the particle density, not the bulk density. Just to
Yeah,
make
it is
sure.
particle.
But
It is particle density.
Okay.
Yes. Yes. The bulk density, we in this training we outline the core method. The core method. I
Yes.
mentioned the cloud method as a traditional old one, and I promise to share it with you. So if you read it and you think that it could be possible to be used in your laboratory, then we can more elaborate on it this way. Yeah.
Yes. Okay.
Okay. I think if there is no, is there any other comment, or we can move to the hydraulic conductivity?
Can we have a break
Yes.
for 10 minutes
For-
or
Okay, we can take
okay,
it.
thank you.
Okay. See you in 10.
Based done. So we are back. Assalamu alaikum. Assalamu alaikum.
Wa alaikum assalam.
We are back. Okay. طيب انا will share with you برضو الطريقه بتاعت الهيدروميتر بالبيكنوميتر.
It is around 10.03. This is second part. You see that we have taken the empty picnometer weight, so that is coming 30.382, and also we have a soil sample which is close to 10 gram. It is around 10.037 gram. So it will be not approximately 10 gram, that is difficult, as close as 10 to 10 gram. Now you take the picnometer out, and then what we are doing is we are now placing the soil inside the picnometer. So we are adding soil. You can use a funnel so that the soil will not so there is no waste. Slowly you do that, and you try to see that the bottom of this funnel should not touch to this. This is every time whenever you are placing soil or whenever you are placing toluene. So this funnel tip, that it should not touch the bottom of this tip. Now, as you see that the soil has been transferred now, so you place the lid, and now we have to take a weight. Why you are taking the weight? Because it may happen that while you are taking it may happen that while you are transferring the soil, there may be some soil which can be you can say fallen outside. So if we take this weight and then subtract this from this empty picnometer, you subtract this from picnometer plus soil, you will get the soil weight, and that soil will be the exact soil weight which is remaining in the picnometer. Now the picnometer now need to be filled up with toluene. Again, please be careful that the tip of this funnel should not touch the bottom of this. Slowly pouring the toluene. Okay, slowly. Do it slowly. As slowly as you can. Okay. Yeah, just 1 minute. Raghuveer, just leave it. So what you can do is that you can do one thing. You can start it a little bit. If you are starting a little bit, just I am starting it gently. You see, so there are spaces within these soil particles. So those spaces should be filled up by toluene. The spaces are all artificial spaces because you have taken a disturbed soil, but nevertheless, when you are taking the soil particles, now pour again, soil particles, so definitely there will be some spaces left out. So as he is pouring the toluene will slowly, pour it, no problem, pour it. A little bit slowly, that's all. More and more. So the toluene, the soil is actually replacing the toluene to that extent of whatever the portion it is occupying. So now you will use the Archimedes principle and then we will calculate. The calculation part I will show in the last of this part, last of this particular particle density demonstration. Okay. Now as you see that he is taking up to this, he's taking, yeah. So yeah, make it to the fullest extent. Now you see here he is placing the, do it slowly so that they can see, placing it slowly, just place it. Yeah, place it. You see some toluene is coming out from the top. So as it is coming out from the top, so from here, so that means now at this condition it is fully occupied by toluene, except those portions. Take it out and then wipe it properly, not like this. Wipe it properly, full, properly full. take more and full. So he's wiping it completely. Yeah. Now you can take the weight. So no, don't write right. So there is one caution that as you can find that, okay, I'm taking this out. So just watch this very closely. So as I am a little bit of shaking it, there may be some bubbles may come out. What are those bubbles? The bubbles are actually those entrapped here within the soil particles. So let me find out whether I can take the. There could be some bubbles which are coming. Yeah, you see, you can find out some bubbles which are coming. So those bubbles are actually all the spaces which are occupied by air. So it is advisable that you keep this picnometer for at least say 10, 15 or 20 minutes, and intermittently you can shake it very gently so that the bubbles will all go away. As the bubbles will go away, there is little bit of toluene will take the place, and so you will be having less toluene. So you need to again fill it up, the rest of the portion which was earlier occupied by the air spaces. So I'm coming to you in the next presentation.
So I think now we can move to the other.
Doctor, why do you use the toluene, not the water?
You can use yes, you can use the water or you can use the toluene, because here also, yeah, you just need to use a liquid with predefined density. Then in the calculation you multiply by the density of that solution. Yeah.
Thank you.
You get my point?
Yes, yes.
يعني يمكن استخدام سوائل غير الماء. لكن طبعا الارخص المويه طبعا، او ممكن تكون available. طيب so we'll move to the last presentation, that to determine the hydraulic conductivity of the soil. And this is a very important physical parameter that to be determined for the soil. What we mean by hydraulic conductivity? Hydraulic conductivity can be it is saturated hydraulic conductivity, and saturated hydraulic conductivity is a quantitative measure of saturated soil's ability to transmit water when subjected to hydraulic gradient. We mean that if you have a soil and you have a water upon its surface, this will provide hydraulic gradient, so that how the water can transmit the water upon its surface. So it is a measurement for easiness of water movement through the saturated soil pores. And of course, this is to some extent is related to the soil particle density and soil bulk density and textures. So soil water is subject to the number of forces: gravity, the Earth's gravity. The water normally move according to the gravity downward, and the hydraulic pressure, and the attraction of soil matrix for the water. How the soil itself bonded the water in it between its pores. The presence of solute and the action of external gas pressure. At any point in the soil, total soil water potential is the sum of all the contributed force: gravity, hydraulic pressure, the soil type. So the movement of water through soil under saturated condition is governed by Darcy law, and which Darcy law is quantitatively describe one-dimensional water flow in saturated soil as written J equal minus Ki, where J is the water flux or flow of water, K is the hydraulic conductivity, and I is hydraulic gradient. The minus sign keeps K positive and maintain directional integrity, and hydraulic gradient always decrease in the direction of the water flow. For simplicity, the minus sign is omitted in the remaining discussion. And Darcy law demonstrated that flux J is proportional to hydraulic gradient, and hydraulic conductivity is constant. That defines the proportionate relationship of flux to hydraulic gradient. The dimension assigned to flux and hydraulic gradient determine those of saturated hydraulic conductivity. Water flux J is defined as J equal Q over AT, where J is quantity of water moving through a cross-sectional area A of the soil per unit of time T. The hydraulic gradient describes the effectiveness of the driving forces behind water movement and is defined as I equal change in H over RL, where change in H is the difference or change in the total water potential between point in the soil, and and L is the length or the distance between the 2 points. The hydraulic gradient is the difference in total hydraulic head per unit distance. For saturated flow, the two primary driving forces are submergence component of pressure head and the gravitational head. As you know that the water is moved downward by force of gravity, in addition to the pressure of head. For example, if you put 1 centimeter water on the soil, this 1 centimeter water on the top of the soil will create pressure to insert or to introduce the water into the soil. In comparison, if you put 2 centimeters of water, this will create a greater hydraulic potential for that soil. So the two primary, they are the head of from gravity and the head from hydraulic potential. So HG, gravitational head, which is vertical position of point relative to selected elevation datum, and gravitational head equals the distance above or below the datum. the relative elevation difference between a point and the datum determines the gravitational head. From any energy perspective, gravitational head is the work required to move water from the datum to its present position. HB pressure head due to submergence, it has a 0 value at the surface of the water table and increase has a positive value with the depth below the surface of the water table. In the Darcy law, saturated hydraulic conductivity is a constant. So the hydraulic conductivity of the soil is constant or proportional constant, and that defines a linear relationship between the two variable G flux and hydraulic potential. If it is the slope of the line E over Y showing the relationship between flux and hydraulic gradient. For solving of Darcy equation for key, this is the hydraulic conductivity yield flux over I. So the flux represents the quantity of water moving in direction of and at a rate proportional to the hydraulic gradient. So there are two main factors, that is the hydraulic gradient and hydraulic conductivity. Hydraulic gradient and hydraulic conductivity. The hydraulic conductivity is constant. The hydraulic gradient is different. If you put, for example, 1 centimeter of water, the hydraulic gradient is different from to put 2 centimeters of water. If the same hydraulic gradient is applied to the two soils, the soil from which the greater quantity of water is discharged, that say highest flux is more conductive, greatest flow rate. Normally, the sandy soils yield a higher flux, and this, of course, related to its bulk density and particle density is more conductive and the presence of porosity than the clearly soil at the same hydraulic gradient. The soil with the steeper slope has a higher hydraulic conductivity. So the hydraulic conductivity or the slope, okay, defines the proportional relationship between flux and hydraulic gradient, or in this case, unidirectional flow in saturated soil. For sample preparation, you try to use 2 millimeter safe air dry soil, but you will try to bring it to the field condition. Somehow, you know, already you know the particle density, the bulk density of the soil. So in general, you try to manage the soil to bring it into a similar condition of the field by adding and making some push or pressing of the soil particles. The apparatus used for hydraulic conductivity, they are soil container, basically soil container, and normally they use a pipe type of soil container like a core. And in the bottom of the core or container, there will be a gauge or brass sheet. And at the top, you have to put some filter paper on the top of the soil. Then you normally, if the system is closed, you have to make a hole in the block to accommodate the outflow tube of the soil container, and also guiding rods are mounted in the block to keep the cylinder vertical and to ensure square impact. And here the container itself in the form of cylinder, soil container in the form of cylinder. As I said, also you have to put a filter paper rock for supporting a number of soil containers, constant level, water supply, and also siphon tube to connect soil container to water supply. If your system is closed, you have to use a siphon tubes. You need a soil grinder to grind the soil, and also mixing close to join the cylinder together if you have another one. So for procedure, the soil is air dry soil, passes through 2 millimeter sieve. The grinder also may be used for hard soil. Then dump the entire sample in one motion into soil container that has been fitted with a screen and filter paper. Filter paper at the top, screen on the bottom of the container. You have to maintain to some extent, as I said, the method of transferring soil is used to prevent particle size segregation. You have to ensure to some extent that the bulk density, the produced bulk density by adding soil is similar to the field condition. And this can be done by backing the cylinder containing the soil, drop 20 times through a distance of 2 centimeters. Place a filter paper on the soil surface and introduce water into the container with minimum of soil disturbance. Then record the time of application of water and, if possible, the time of initial outflow. Collect the percolate in a suitable receptacle and measure the volume at a convenient time. This test ordinarily are run until the volume of water that has passed through the soil corresponding to approximately 12 centimeters. The calculation of hydraulic conductivity require some plotting or graphing of accumulated equivalent depths of percolated with time, and flux. With soil having extremely low percolation rates, an attempt should be made to obtain at least one flow measurement, and time rather than depth of water is used to determine when to discontinue test on such soils. There is some remark that soil satisfactory results are not obtained unless the height is less than the diameter of soil column. So when you use a column, you have the height should be less than the diameter of soil column or cylinder. And this is particularly important if soil is well appreciably on wetting, and this of course for clay soils. And from that experience indicates that cylinders should have at least a 7.5 centimeter diameter for a 5 centimeter depth of soil. The hydraulic conductivity is affected by the temperature, as we mentioned in many other physical measurement. As you remember, for the texture, we have the correction factor for temperature. So the temperature range from 18 to 24 degrees centigrade. The effect of temperature on hydraulic conductivity in this range is small compared with the effect rising from such factor as quality of water and the base status and salinity of soil. The hydraulic conductivity, of course, because it deals with the solutions, so the the quality of water has some pronounced effect, because it also will make some modification for viscosity of the water. And of course, the salinity, it has also some effect on the hydraulic conductivity. Therefore, correction for viscosity effect on measurement and temperature other than 18 can readily be calculated, but it has been observed that temperature has other and not always predictable effect on the hydraulic conductivity of soil, in addition to those arising from viscosity. Here is more emphasis on impact of temperature on hydraulic conductivity. The hydraulic gradient is usually set in the range from 1 to 4, although values as high as 10 do not seem to affect the result significantly. In general, the water that will be used on the soil in the field should be used for the laboratory determination. Here, Flari always ask about water quality. Here in this test, to have a reliable measurement, it recommended to use the water that in the field, not distilled water or deionized water. Here to maintain a realistic measurement of soil hydraulic conductivity, it is advisable to use the ordinary water that used in the field or in the farm. Measurement always made in triplicate. The samples are discarded and the test repeated if the range of value is greater than 50% of the mean hydraulic conductivity. Here, this is the figure showed the major forces that cause the movement of water through saturated soil. Here, this is the gradient pressure come from the water, and this one is gravitational pressure, and here the length of soil column, and submerged pressure is come from pressure from the water and pressure from gravity, and this is the datum plane. So the total hydraulic head at inflow equal to that head of water and the gravitational one. The difference in head, that at the datum here, the pressure is equal to 0. Total hydraulic head at outflow equal to 0. So the difference equal the submergence head minus 0, which is equal to H of water and H of gravity. So the hydraulic gradient equal I, the hydraulic gradient equal change or difference in head over the length. And this equal the head of water and the head from gravitational. For calculation, the flux equal minus hydraulic conductivity multiplied by hydraulic gradient. The flux, as we mentioned, equals the quantity of water that pass through the soil and saturated soil divided by area of this column multiplied by time. And hydraulic gradient equal difference of the head over the length. And here you in this graph you can see that the sandy soil had is higher than the clay soil in the term of the slope, the angle. So the sandy soils have a greater hydraulic conductivity in comparison with clay soils. I know this part is little bit mathematics and complicated. I will end with showing you in a video showing that the hydraulic conductivity in the lab.
Good morning. Today we're going to demonstrate how to measure the hydraulic conductivity of different materials. Hydraulic conductivity determines how quickly water moves through the soils in a catchment to groundwater storage for a stream. Hydraulic conductivity controls the ease at which water will flow through porous media and is important locally and globally for drinking water extraction, contaminant transport, flood control, and many other aspects of daily life. Using a special equipment called the Darcy permeameter, we can determine this by the falling head method or a constant head method. We will demonstrate the constant head method on the material, and the volumetric discharge will be measured from the outflow. By knowing the volumetric discharge, hydraulic gradient, and surface area of the sample, the hydraulic conductivity of each material can be determined through the rearranged Darcy's law. The principle of the constant head method relies on getting a constant laminar flow of water through the soil sample, from high elevation to low elevation. The sample must be well packed and saturated with water before the experiment begins. The samples have been sitting in water to become saturated, and note that there's a space between the material and the top of the ring. For our experiment, we will be adding water to the Darcy permeators until 500 milliliters has been used, or until 15 minutes has been out. On the table, we have all the equipment on display to demonstrate this technique. We have a 500-meter graduated cylinder filled with water, which is used to measure how much water we use. We also have a beaker filled with water here. We have rulers to measure the volume of the Darcy permeameters, a stopwatch to time the experiment. We have a data sheet here with all your calculations or your observations on it. And then we have our Darcy permeameters in here, filled with different substrates. Right now they're sitting in water to keep them saturated. And over here we have a bucket and a 2 millimeter sieve. The bucket is to catch the water that goes through the permeameters. To calculate hydraulic conductivity, you need a few measurements from the Darcy permeameter. First, you need to know the sample height. So we get that from measuring the total height, which is 6.5 centimeters, and then subtracting the space between the substrate and the top, which is 1.5 centimeters. And then you'll also need to know the sample surface area, and to calculate that, you need to know the diameter of the Darcy permeameter, which is 7.5 centimeters. It's important to be organized and ready for the constant head method. Place the sample on top of the bucket and sieve. We're starting with sand. With the 100 ml beaker, fill to the brim with water, being careful not to overflow. And then activate the stopwatch. the water filters through, use the graduated cylinder to continuously fill the Darcy permeameter with water. Every time you fill the Darcy permeameter, record the time and how much water is added. So I'm going to add water now. The time is 28 seconds. So I'll record 28 seconds and then record how much water we used. The time is now 1:28, 1 minute 28 seconds, and I'm going to fill again. Okay, so I've added water 7 times so far. I'm going to add again, and the time is now 6 minutes 30 seconds. So I've done 12 measurements so far, and I'm going to add water for the 13th time, and the time is now 11 minutes and 32 seconds. And our graduated cylinder is now at 125 milliliters. Okay, so we're on our 17th measurement. I'm going to add water now. The time is 14 minutes and 58 seconds. We've placed our sample on top of the bucket and sieve. We're doing clay this time. With our beaker of water, we're going to fill the Darcy permeameter to the brim and careful not to overflow it. And then we'll start our stopwatch. As the water filters through, we'll use the graduated cylinder to continuously fill the Darcy permeameter with water. Every time we fill the Darcy permeameter, we will record the time and how much water has been added. So now we'll do the first measurement. So we'll add water from the graduated cylinder. And we'll record the time. It's at 2:25 minutes. And now we'll do our second measurement. The time is 5 minutes and 20 seconds. We're going to do the 7th and final measurement now. And the time is 15 minutes. We've placed our sample on top of the bucket and sieve, and we're doing glass beads this time. So with your beaker of water, fill the Darcy permeameter to the brim. Careful not to overflow it. And then start the stopwatch. As the water filters through, we're going to use the graduated cylinder to continuously fill the Darcy permeameter with water. Every time we fill it, we will record the time and how much water is added. So we're going to add water and do our first measurement. The time is 3 minutes and 13 seconds. Okay, we'll do our second measurement now. The time is 5 minutes and 23 seconds. And we'll do our final measurement here, which is our 7th measurement. The time is just about 15 minutes.
So this is the reading, time, minute, time in minute and second, time in minute, time in second, remaining water, the water used, the volumetric discharge, we just divided this volume by time, this one over this, to have the hydraulic gradient. Then when you have the hydraulic gradient, actually the head of soil is around, I think, 6.6, then you can go to the calculation. As it is mentioned by in this video, the hydraulic conductivity is very important soil parameters, especially for irrigation schedules, and also for determination of possibility of water to store, also still the water, and to prevent the runoff. You know that the runoff make a lot of problems if the soil hydraulic conductivity is very low, so the possibility of causing floods and all this will be expected to occur. The floor is yours. السلام عليكم.
Thank you دكتور. بما انه شيء جديد علينا ف ما بعرف، ما في سؤال لحد هلا محدد. لا اذا حدا عنده غير ما بعرف.
بتعملوها عادي ولا
نحن ما بنعملها. ما بنعملها. ما بنعملها ولا مرة. لا ولا مرة حدا طلبها، يعني ماني مذكرة حدا طلبها منا.
وطبعا من المقاييس المهمة للتخطيط لعمليات الري.
ما عندي فكرة إذا بفرع الري بيعملوا هيك شيء، يعني قبل ما إنه في أشياء بتنعمل عندهم باللابس، بس ما بعرف إذا عم يعملوها أصلا يعني.
يعني مهمة في عملية الري، ومهمة في تحديد الكميات حتى نفسها، والتخطيط للفترات بتاعت الري. هو فكرته ببساطة إنك يعني في صفة اللي هو الجزء بتاع الهيدروليك كوندكتيفيتي، وهو مرتبط بنوع التربة المحددة. يعني أي تربة عندها هيدروليك كوندكتيفيتي ثابتة، اللي بتغير الهيدروليك جريدينت. يعني أنت لو مثلا إنك ضفت كمية من المويه كثيرة عملت هيد، بالتأكيد بتضغط على أساس إنه المويه تدخل في التربة. فعلى حسب كمية الماء المضاف بيبقى الضغط الناتج من الماء، لكن من الماء لدخول الماء إلى التربة. لكن الهيدروليك كوندكتيفيتي هو صفة ثابتة لكل تربة. يعني التربة الطينية عندها هيدروليك كوندكتيفيتي ثابتة، والرملية عندها ثابتة، لكن بتغيروا في كمية المويه دي. مثلا لو أخذنا مثال، لو أنت ضفت ماء نفس الكمية، مثلا ضفت مثلا 100 مل أو 100 مل من المويه لتربة رملية، ونفس ال 100 مل من نفس النوع بتاع الماء لتربة طينية، بيحصل تسريب أسرع، أو بيحصل تسرب أسرع، أو مرور أسرع للماء في الرمل مقارنة بالطين. فهنا
it can be estimated from the soil texture.
Yes.
Okay.
من الخصائص يعني الفيزيائية الناس بيدرسوها، خاصة برضو مثلا في الجزء السيفل انجينيرنج، برضو بيهتموا بدراسة الهيدروليك كوندكتيفيتي، لأنه بتوري إلى أي مدى مثلا المياه ممكن تسحب إلى الجزء الأسفل، إلى المياه الجوفية، إلى أي مدى بيحصل لها. يعني مثلا لو يعني في أمطار نزلت، إلى أي مدى المياه المتكومة أو المتكونة من الأمطار هيحصل لها percolation أو يحصل لها تسرب داخل التربة. فالهيدروليك كوندكتيفيتي من المقاييس يعني اللي بيشتركوا فيها للزراعة بالإضافة للإنشاءات الهندسية. يعني لو ما تأكدت من الهيدروليك كوندكتيفيتي ما بتقدر تعمل برنامج بتاع تخطيط للري يعني. هي طبعا الفلكس سهل، يعني انت لو نزلت كمية من الموية مثلا 100 مل أخذت زمن مثلا 10 ثواني، إذا الفلكس يساوي 100 على 10 يساوي 10 مل في الثانية. الاريا الكروس سكشن او الاريا اللي انت اضفت فيها الماء دي هي اللي بتتخطى مع بعض. عشان كده الفلكس بيساوي الكوانتيتي اوفر الاريا في التايم. طبعا هي بصراحة عندها أكتر يعني عندها تو ميثود أساسية. يعني ممكن يكون كونستنت هيت، يعني اللي هي في الفيديو ده استخدمت الكونستنت هيت، يعني كمية من المويه اللي بتكون موجودة فوق سطح التربة بتكون ثابتة. في طريقة تانية ممكن هنا ما يكون ثابت، الكونستنت هيت ما ثابت. بوث اوف ذم يعني الطريقتين ديل هم الناس بتم قياسها يعني. لكن بتدي الهيدروليك كوندكتيفيتي از كونستانت دايما. الفولين هيد معناها كميه المويه جايه من ارتفاع عالي او ارتفاع مختلف. على حسب ارتفاع بتاع المويه بتكون القوه بتاعت دي زي نتكلم عن الاستاتيك انرجي والاكتيف انرجي في الووتر. يعني المويه لو كانت ستاتيك يعني حمل الماء بيكون فقط هو ثابت. مرات بيكون ممكن برضو يجي مثلا لو مثلا عندك خزان ارتفاعه من الأرض 5 متر، وخزان آخر ارتفاعه من الأرض مثلا 3 متر. الخزان اللي ارتفاعه 5 متر بيكون الضغط بتاع المويه بيكون أعلى من الارتفاع 3 متر. فهنا بيكون في الفولين هيت هنا ما ثابت، انما انه بيحصل له تغيير على حسب ارتفاع مصدر الماء. هو الهيدروليك كوندكتيفيتي هو من الفيزيكال بارامترز، عشان كده بياخد الجانب الفيزيائي اكتر. يعني الناس اللي ما عندهم انترست في السويل فيزيكس بيحسبوه يعني ما تقيل شوية. كلاري
يس دكتور، هي اليوم
يعني الفترة اللي فاتت كلها بنتكلم عن السويل كيمستري، لأنكم انتوا البيزك بتاعكم سويل كيمستري، البيزك بتاعكم كيمستري بتكونوا شعارين بانترست، لكن لأنه
عملنا
اليوم
ريفرشمنت للفيزيكس هلا إلى حد ما.
لا هو فيزيكس بشكل أساسي، طبعا فيزيكس سويل فيزيكس، لكن مهمة طبعا لأنه الخصائص بتاعت التربة الجزء الفيزيائي والجزء الكيميائي. صح الناس بيكون تركيزهم أكتر على الجزء الكيميائي، لكن الجزء الفيزيائي مهم جدا. في خاصة هو مرتبط دائما الجزء الفيزيكس مرتبط بالفراغات الموجودة في التربة وعلاقتها بالماء وعلاقتها بالهواء. طبعا مهمة لأنه السويل فيزيكال كونديشن مهمة بارتباط رئيسي بتوفير للمياه وتوفير لهواء كافي للنباتات وكده.
ثانك يو دكتور، هي انترستنج، بس نحن لانه مش عم نشتغلها مثل ما قالت ماري، كرمال هيك ما كثير كان عندنا تفاعل واسئله عليها. بس انه
لا هي بقى هي
فهمناها هلا.
انا متوقع هيك، لكن طبعا لانه انتم معامل بتاع التربه، يعني على الاقل لما تاخذوا فكره عن الاشياء دي، ان كيس انها طلبت او ان كيس انه
ايه صحيح،
الناس تكون عندها فكره اساسيه عنها. هي لو لاحظتوا كميثودولوجي ما صعبه، يعني كميثودولوجي ما صعبه. انت بتدخل تجهز سلندر، احنا عاده يعني هو نفس الطريقه اللي اشتغلت بها في الفيديو. جهز السلندر بتملاه بالتربه، بتعمل له يعني حقيقة بتعمل له رج أو ضرب على السطح بتاع الطاولة على أساس تومنتين، أو تحاول تجيب ظروف بتاعت bulk density مناسبة للفيض. بعد ذاك بيكون في فلتر بيبر، بعد ذاك بتضيف كمية موية وبتشوف المويه بتتسرب كيف. المسألة اللي يمكن تكون مهمة، المسألة بتاعت انه السويل ساتوريتد. السويل ساتوريتد معناها هي تربة مشبعة بالماء، يعني ما تربة شنو، يعني حركة المياه هنا في تربة اصلا بيها شنو، بيها ماء ما جاف. بعد ذاك بتشوف كمية المويه اللي انت بتضيفها بتاخد كم من الزمن. يعني اذا ضفت 100 مل مثلا، كل مرة 100 مل 100 مل، بتشوف ال 100 مل بتمر كم في الزمن، تاخد كم من الزمن حتى تمر من خلال السويل. طبعا السلندر اللي انت استخدمته عنده اريا مساحه بتجيبها، دي اللي هي الكروس سكشنال اريا بتاعته، بتبقى الكوانتيتي يعني الهيدروليك جريدينت اللي هو الكوانتيتي اللي بتمر مقسومه على كوانتيتي من المويه اللي بتمر مقسومه على المساحة بتاعت السلندر في الزمن اللي أخذته. بعد ذاك بتعمل جراف فوق كمية المويه المرت والهيدروليك جريدينت تحت. من الجراف ده بيجيك ميل، الميل ده هو بيساوي الهيدروليك كوندكتيفيتي. فكميثودولوجي ما معقد، يمكن الجزء النظري بتاعه صح، يعني في ايكويشن كثيره وهنا، لكن دي الفكره الاساسيه بتاعته. الجانب العملي زي ما تكلمت مهم فيه، انه هو بيحدد مدى قدره التربه على انفاذ او على تمرير الماء، ودي مساله مهمه من ناحيه بتاعه الري. انا كنت من تضيف ماء، انت داير تضمن انه الماء دي بيتم لها تمرير داخل التربه. لو اضفت مويه اكثر من قدره التوصيل الهيدروليكي للتربه، حتكون قاعده على السطح، حتعمل ما يعرف بالوتر لوجين او الغمر. بالتالي النبات بيكون شنو، قاعد في ظروف ما فوق اكسجين مناسب. ممكن دي تؤدي زي ما عارفين القمره والوتر لوجين ممكن تؤدي ل انه النباتات ما تنمو في بعض المحاصيل كثيرة جدا، ونباتات حساسة للوتر لوجين. برضو من ناحية هندسية زي ما قلت مهمة، لأنه أنت التسرب بتاع المياه هيأثر على الأساسات بتاعت المباني، هيأثر على البنيات الأساسية زي الطرق وغيره. فالهيدروليك كوندكتيفيتي من الخصائص الفيزيائية المهمة في المجال الزراعي وفي المجال الهندسي. في فيديوهات برضه زي ما قلت الطريقة في الفيديو الأول دي كانت بيعتبروا constant head of water، يعني في ضغط مياه ثابت، لكن ممكن تاني في طرق بتقيسه وهو حاصل له فولين. فما أعرف لو حابين ممكن نشوف فيديو تاني، أو إذا حسيتوا إنه الموضوع ده كده بالنسبة لكم كافي، على الأقل ممكن تعملوا فيه اطلاع إضافي يعني. أي كومنت؟
ما في مشكلة دكتور، إذا بحب تفرجينا فيديو تاني no problem، ناخد فكرة تانية وهيك تتركز الفكرة أكتر براسنا كيف بدنا نعملها إذا اضطرينا، إذا انطلبت منا.
This is a tutorial for the Hydraulic Conductivity Lab of the Geotechnical Engineering course Civ E3208. The purpose of this lab is to determine the hydraulic conductivity of a soil sample. Hydraulic conductivity is a property of the soil which determines the rate water will pass through it. It is important to be able to know how to measure hydraulic conductivity, as it is a factor in applications like dam and landfill design. There are two types of hydraulic conductivity tests: the constant head test for coarse-grained soil like sand and gravel, and the falling head test for fine-grained soil like silt and clay. This is the apparatus for the constant head test. Connected to this reservoir are three lines: an intake, which is connected to a tap and will keep filling our reservoir; a discharge line, which will take extra water out of the reservoir and keep the water level constant; and a line with a valve which connects to the test cylinder. First, obtain about 1 kilogram of coarse soil and place it in a container. This should be enough to fill the test cylinder. Record the mass of the container plus the soil in a table. Place a screen at the bottom of the cylinder. This prevents the soil from being carried out. Fill the cylinder with the soil sample. Split the soil into about 3 layers and compact each layer with a hammer, like this. If your objective is to determine the conductivity at a specific density, measure the mass required given the volume of the cylinder and compact the sample enough so that it completely fills the cylinder. The top surface of the soil in the cylinder should be level with a small space for the screen and end cap. Place the screen on top of the soil as well as the separator. Next, place the cap on top of the cylinder and secure it with 3 screws like this. Record the mass of the container plus the remaining soil. Connect the intake line from the reservoir to the barb at the top of the test cylinder. And connect the tubes for the 2 manometers to the 2 outlets on the side. These are for measuring pore water pressure at specific points. Before filling the reservoir, close the valve on the intake of the test cylinder. Turn on the tap and let the reservoir fill up. Once the level of water in the reservoir reaches a certain level, it will start to discharge into the sink. When this happens, the level of water is constant, and we can begin the test. Now open the valve to let water into the sample. Before we start measuring flow rate, we need to let water run through the sample. This is to remove any trapped air. Let the water run through the system for a few minutes. Here we can see the pore water pressure being recorded on the 2 manometers. Now we can start measuring water flow rate. Take a beaker like this one, then measure and record its mass in the table. We'll be using this stopwatch to record the time. Simultaneously start the stopwatch and begin filling the beaker with the discharge from the test cylinder. Here we are aiming to collect about 300 milliliters of water. Simultaneously stop the stopwatch and remove the discharge. Now record the mass of the water plus the beaker, as well as the time it took to fill in seconds. Empty the water and zero the stopwatch to reset. Repeat this test 2 more times, each time aiming for a different amount of water. Before we finish, we need to calculate the head applied to the sample. To do this, measure the total head at each manometer from the base of the cylinder. Here, the head height of the top manometer is 49.8 centimeters and 11.3 centimeters for the bottom manometer. Finally, record the difference in height between the outlets to the 2 manometers. You can draw a line around the outside to help you do this. In our case, this was 16 centimeters. We can now clean up the apparatus and proceed to the calculations. Calculate the cross-sectional area of the cylinder. To do this, take calipers and measure the diameter. From this, we get the cross-sectional area, as the section is circular. The coefficient of permeability for the constant head test is given by this equation, where Q is the volume of water collected, L is the sample height, A is the cross-sectional area of the soil specimen, H is the total constant head, which is the difference in head between the 2 manometers, and T is the duration of water collection. Calculate K for each of your 3 tests. And finally, calculate the average of these 3 to get the final value for conductivity. For the falling head test, first we need to put together the test cylinder. Unlike with the constant head test, which uses a screen, the falling head test uses a porous stone. Place the porous stone on the base, like this. Now place the tube which acts as the cylinder's walls over top of it. Then thread the end cap with a hole in it onto the 3 protruding screws. Secure it with 3 nuts. This is to create a tight seal. Now obtain a soil sample. Similarly to the constant head test, measure out approximately 1 kilogram of soil into a container and record the mass of the container plus soil. Place the soil in the test cylinder like this, again compacting the soil into about 3 layers. In this experiment, we are using a fine-grained sand, although this test is best done with silts or clays. Level the soil at the top of the cylinder. Place the second porous stone on top of it, and then thread the end cap on, securing it like this. Finally, record the mass of the soil container plus the unused soil. The cylinder for the falling head test consists of just one line connected to the test cylinder. Connect the line to the cylinder. Before we can start the test, we must saturate the soil with water. There are 3 valves in the system. Make sure they are all open. Start adding water to the top of the standpipe. A larger funnel can help you do this more easily. As you can see here, water will start moving into the test cylinder and saturating the sample. When water starts coming out of the nozzle at the bottom, as you can see here, we can proceed. If there are bubbles in the pipe, gradually add more water to the system so that the air can be flushed out. Close the valve at the top of the test cylinder so that the water level in the pipe remains constant. If there is water left in the funnel, open and close the valve so that the level of water in the pipe falls to a measurable level. For the first test, use a stopwatch to record the time it takes for the water to drop a certain distance. Start the stopwatch and open the valve simultaneously. Wait for the water level in the pipe to drop a given distance. Close the valve and stop the stopwatch simultaneously when the new level is reached. Record both levels of water, as well as the time in seconds it took for the water level to drop. If the water level is too low, add more. Repeat this test 2 more times for 3 readings in all. This is the equation for the coefficient of permeability when performing the following head tests. Lowercase a is the cross-sectional area of the stand pipe. The internal diameter is given to us as 6.6 millimeters. From this, we get the area. L is the length of the soil column. In our case, the length of the column is 16 centimeters. Uppercase A is the cross-sectional area of the soil column. In our case, the diameter of the cylinder is 6.3 centimeters. Therefore, the cross-sectional area is 31.2 square centimeters. T is the length of time taken for the head to drop. H0 and H1 are the total head before and after each test, respectively. Calculate K for each test. Finding the average value of K between all 3 of our tests gives us the hydraulic conductivity. This concludes the following head test and the hydraulic conductivity lab.
So in this video, you see the both methodology, constant head and falling head. Here in our laboratories, normally we use the constant head. But I think the falling head is easier, isn't it? Any comment?
No, doctor, but the first video, it was easier.
And falling.
Yes.
It's easier, yeah?
It can be conducted in our lab. We don't need special materials.
Yes, yes. Yes. Even these cylinders, you can use even PVC pipe. It is not that difficult. Yeah.
Yes,
Don't
yes.
worry about the.
Yes.
You can use a normal cylinders, PVC cylinder with non-diameter, and you add the water. You add the soil, then you add the water and identify the time for passing of water. Yeah, the methodology is very easy, really.
Yes.
At least if it يعني لو في حد طلبها منكم بعد ده بقيتوا اخذتوا فكرة عنها كويسة، يعني ممكن ما تكون حتى التضريب بتاعها سهل، الكالكوليشن يعني ما معقد شيء يعني.
في available SOP لا جاهز عندكم أو بعده under writing؟
نعم.
في SOP للميثود hydraulic conductivity؟
لسه. ولا البروسيس بتاع الستاندرد اوبريتنج بروسيجر بياخد لونج تايم. يمكن فلاري تكون قاعدة تدخل في الاجتماعات دي حاليا. يعني في آخر اجتماع حتى الطريقة بتاعت البارتيكل density as a picnometer to be يعني standardized اقترحت في آخر اجتماع يعني. في الجزئيات بتاعت الفيزيكال يبدو إنه لسه أفتكر دار جهد يعني لسه ما تم إعدادها. آخر اجتماع كان عن العام الحالي إنه الفيزيكال بارامترز اللي حتدخل البارتيكل دنسيتي بطريقة البيكميتر ميثود.
اوكي.
اليوم فيزيكال بارامترز. البارتيكل دنسيتي والبالك دنسيتي لأنها to some extent في الكيمستري الناس بيهتموا بيها لأنه بتكون في الليكويد برضه، كده كان الانتراكشن كان مطلع. لكن الهيدروليك conductivity is pure physical parameter يعني. ما جاتكم رغبة تجربوها يا ماريا؟
من الوقت الحالي لا، بس انه في حالة طلبت ما بعرف اذا انا بدي اسال اذا بالإيريجيشن ديبارتمنت عندهم اياها عم يعملوها او لا، لانه في ديبارتمنت للإيريجيشن ففي مفروض في بارامترز بينعملوا عندهم.
على الأغلب بيكونوا لازم يعملوها للسويل يعني.
Yes, I will ask.
Okay, let me know.
Okay.
دكتور.
نعم.
أنا عندي سؤال شوي ضغط.
تفضلي.
بالنسبة نحن البورز بالسويل هن بيمرروا المي وبنفس الوقت بيعملوا ستورج للمي، يعني قصة إنه تمرق المي إذا كان عندي بورز كتير تمرق أسرع. بس فكرة الستورج وين بتتجمع المي بقلب التربة؟ يعني لما تكون ساتوريتد بيصير عندي ران اوف مفروض.
لما يكون ساتوريتد والهيدروليك كوندكتيفيتي طبعا يعني هي التربة نفسها بتكون على أعماق مختلفة، بيكون في اختلاف في الهيدروليك بتاعها. يعني مثلا إذا أنت حصل ساتوريشن لل 10 سنتيمتر الطبقة العليا، 10 سنتيمتر العليا، ال 10 سنتيمتر التحت منها بيكون في اختلاف في الهيدروليك بتاعها، فالمويه هتتحرك من البريشر العالي للبريشر المنخفض، فهي هتتحرك داخل البروفايل. يعني الووتر هيد هيتحرك، فدايما بيكون في حاله بتاعت انه في حركه بتاعت مياه في الداون وورد موفمنت. فالجزء الاعلى دايما لو جيتي مثلا عينتي للتربه هتلقى الجزء الاعلى دايما هو بيكون اكثر جفاف من الجزء الاسفل، المويه بتتحرك. فهنا الهيدروليك كوندكتيفيتي هي بتقيس الى اي مدى التربه نفسها البورس بتاعتها دي هي بتقدر بتمرر الماء. فده دي الفكره بتاعت الهيدروليك كوندكتيفيتي. لكن بالتاكيد البورس هي نفسها ما بتكون مليانه كلها دوما، يعني لازم يكون في جزء فيها ما فيه مويه على اساس انه تحفظ التوازن بتاع الماء والهواء. الووتر لوجن لو التربه توتالي ساتوريتد كومبليتلي ساتوريتد هيكون كل البورس مليانه بالمويه، ما في هواء، ودي بتخلق مشكله. لكن دائما اللي بيعمل بالانس للمساله دي الحركه بتاعت المياه نفسها من طبقه الى طبقه اخرى.
اوكي وضحت الفكره. انا تخيلت انه كل البورز امتلوا مي، فكيف بده يكفي المرور
دكتور فاليري بتعتذر ما عندها انترنت، بطلت معنا بالميتنج. مشكلة كهرباء أكيد أو شيء.
عذرة مقبول، والحمد لله يعني هي يعني حضرت كل المطلوب، حتى بيكون بيبقى بس.
يعني هلا انا بس بدي ادرس الهيدروليك، مش لازم ادرسها على طبقه واحده، لازم اخذ البروفايل كله ادرس الهيدروليك.
بالضبط الهيدروليك كوندكتيفيتي بتدرس لكل الطبقات بتاعت التربه على اساس تضمن الحركه تحت المياه في السول
لحد ما توصل للمياه الجوفيه.
يعني على الاقل هو دائما ناس الجيوفيزيكس، لو لاحظتوا هنا الاخير ده جاي من ناس الجيوفيزيكس، ناس السيفل. يعني السيفل بياخدوا قراءات لحد 3 متر، لكن ناس السويل عاده بيهتموا لحد 1.5 متر عشان انت تضمن انه يعني what will going on especially زي ما قلت. الفكره الاساسيه هو الهيدروليك كوندكتيفيتي بالنسبه للزراعه، وهو مهم في المساله بتاعت الirrigation. يعني بالضبط انا لو اضفت للحق مثلا 10 سنتيمتر هيد، يعني ارتفاع بتاع مويه فوق سطح الارض 10 سنتيمتر، هل ما هو الزمن الكافي لمرور هذه الكميه من المياه الى داخل التربه؟ وبعد ذاك حتى لو دخلت داخل التربه بتقوم بتعمل مويستن لكم دبس، كم سنتيمتر داخل التربه تحت، على اساس انه لو ضفت مويه اكثر من طاقه التربه للتوصيل بيحصل عمليه بتاعت شنو؟ انه التربه بتكون مغموره بالمياه، ودي طبعا ما مناسبه. وبالاضافه لكده ما بتزيد الووتر يوز افشنسي او كفاءه استخدام المياه. فمثلا التربه لو تربه طينيه مثلا انا بضيف لها كميه بسيطه على اساس انها هي الهيدروليك كونكتيفيتي بتاعها بسيط، بعد ذاك هي بتحتفظ بالكميه بتاعت المويه دي بشكل كويس لما تدخل لها، مقارنه بتربه رمليه انا لو ضفت لها كميه هي حتسحبها بسرعه، بالتالي انا هحتاج اعمل ري في فترات متقاربه، ما بيعرف بالirrigation سكيدولز، عمليه جدول الري. يعني انت مثلا من تقول لمزارع اسقي كله اعمل اسقي او اضيف ماء ري كل اسبوع دي بتختلف بحسب نوع التربه. في ترب ممكن تقول كله 15 يوم، كله 14 يوم، في ترب انت بتسقي كل اسبوع. لكن في الحاله دي كميه المويه بتسقي كل اسبوع، كميه المويه بتكون اقل من اللي انت بتضيفها انها تسقي كل اسبوعين وكل 14 يوم مثلا. فهي في الجدول بتاع الري، عمليه تنظيم الري، الانترفلز الفترات الري، الايام التي بعد كم من اليوم يتم عمليه الري دي، بالاضافه لكميات الماء المضافه عند كل ريه بتعتمد على الهيدروليك كوندكتيفيتي بتاعت السويل. وطبعا زي ما قالت ماريا الهيدروليك كوندكتيفيتي عنده علاقه بالبلك دنسيتي، عنده علاقه بالبارتكل دنسيتي، وده بالتاكيد عنده علاقه بالتكشر وكده. يعني دي كلها خصائص فيزيائيه لو لاحظتوا اليوم، وكلها خصائص فيزيائيه مرتبطه مع بعضها البعض. طبعا التكشر بتعتبر من الخصائص الفيزيائيه برضه، يعني دايما التكشر، البلك دنسيتي، البارتكل دنسيتي، الساتوريشن بيرسنت بتحسبوها مش كده؟
saturation percent لشو؟
ساتوريشن بيرسنت لانه بتشتغلوا ساتوريشن بيرسنت برضه دي خاصيه فيزيائيه. الساتوريشن بيرسنت دي انتم ما بتحسبوها لانكم انتم بتشتغلوا بالسويل ووتر سسبنشن، يعني انتم بتضيفوا 1 to 5 صح؟ لكن لو انت عملت السويل بيست انتوا ما قاعدين تعملوها، يعني بتعمل اكستراكشن السويل بيست اللي هو مثلا انت بتضيف بتجيب كميه من التربه سي 250 ملي 250 جرام اير دراي سويل، بتقوم تضيف لها كميه من الديستيل ووتر الى ان يحصل لها ساتوريشن، تشبع، كميه بتاعت مويه كافيه لكن ما تكون اوفر. بعد ذاك بتحدد كميه الماء التي اضفتها دي، بتديك وتنسيبها للوزن الجاف في الفرن، دي بتديك ما يعرف بالساتوريشن برسنت، كمية الماء التي كافية لتشبع التربة. الساتوريشن برسنت والتكشر والهيدروليك كوندكتيفيتي دي كلها بتعتبر خصائص فيزيائية. الهيدروليك كوندكتيفيتي لو سمحتوا لي برضو هو برضو بتقاس بطرق تانية يعني شبيهة، أو في حاجة اسمها الانفلتريشن ريت، معدل التسرب. معدل التسرب عادة الناس بيعملوه حقل، يعني في الحقل نفسه بيعمل معدل التسرب، هو نسبة مرور برضه نسبة أو قدرة التربة على تمرير الماء. طريقته كمان أسهل يعني أبسط كثير، لكن فيلد ميثود يعني. الفكرة كده وضحت؟
ايه ثانك يو، واضح.
ثانك يو.
ويلكم. هي لو يمكن نكون اسري، يمكن ماريا لو بكره ممكن نعرف انه اسري لو بيشتغلوا الحاجات دي بيكون معناها جزء من المعامل بتاع التربه متخصصه بس في الري. دي بتكون على الاغلب بتكون بتجري كل الاختبارات دي بتاعت الانفلتريشن ريت والهيدروليك كوندكتيفيتي.
ايه راح اسالهم وشوف اذا بيعملون او لا. هلا بس هن اكيد بيعملون للتجارب يلي بتنعمل ضمن المصلحه، اللي خاصه بالمصلحه، ما بتنعمل للمزارعين. يعني هيدي الخدمه منا اوبن، مثل عنا بنعمل فحص التراب روتين، يعني هؤلاء شغلهم هن الخاص. اذا كانوا بيعملوها بتنعمل لشغلهم الخاص، للتجارب اللي بتنعمل ضمن الفرع او ضمن المصلحه كمصلحه، يعني كل الفروع الثانيه اللي بيطلبوهم اكيد، لانه هن بده يكونوا بيتنسقوا بين بعضهم كرمال قصه الري تنعمل او لا. يعني المزارعين ما بيقدروا يعملوها، هيك قصدي، يعني منا خدمه لكل العالم.
هي من الاختبارات. هسه مثلا احنا في معاملنا، يمكن لانه انا اعتقد انه برضه كلام طلال درويش دكتور طلال انه الزراعه في وقت من الاوقات كانت بالنسبه للبنان ما بتعتبر ماخذ الاولويه الاولى. ده في الريبورت غايته، ممكن فلاري برضه كانت موجوده يعني. الجزئيه بتاعت انه لبنان كان مهتم بالسياحه اكثر، يعني يا دوب بدوا يهتموا بالزراعه. لكن الهيدروليك كوندكتيفيتي او الانفلتريشن، لو ما الهيدروليك كوندكتيفيتي في حاجه اسمها الانفلتريشن ريت، معدل التسرب، هو من المقاييس يعني المهمه في التخطيط الزراعي ومهمه في الري، لانه حاليا مشكله المياه مشكله كبيره جدا. يعني الزراعه بتستهلك 80% من كميه المويه، يعني المستهلك الاكبر للمياه هو الزراعه. فالقياسات المرتبطة بالمياه، الهيدروليك كوندكتيفيتي، اورال انفلتريشن ريت، اورال ساتوريشن برسنت، دي كلها بارامتر مهمات لتخطيط كمية المياه التي يمكن استخدامها في المزرعة. يعني احنا مثلا في السودان في المعامل بتاعتنا، يعني الانفلتريشن والهيدروليك كوندكتيفيتي من القياسات اللي بنقوم بها، يعني من الجنرال ميجرمنت، يعني من الحياة اللي بنعملها، يعني إن كيس إنه خاصة لو مشروع يعني حتى المشاريع الزراعية العادية بتاعت المزارعين هنا الناس بيعملوا فلتريشن ريت وبيشوفوا معدل التسرب وكمية المويه، على أساس بعد ذاك الإنجينير الزراعي يعرف إنه كم يستخدم من كمية المويه وكده في عملية الري. لكن أعتقد إنه it is good experience رغم إنها هنا شوية بالنسبة لكم، لكن إذا الاهتمام بالزراعة زاد في لبنان بالتأكيد في مرحلة من المراحل حتبقى دي واحدة من الاختبارات. ما لابد الهيدروليك كوندكتيفيتي، لكن ممكن تكون الانفلتريشن ريت واحد من الاختبارات المهمة بالنسبة للمزارعين. أعتقد إنه برضه لبنان من الدول اللي فيها سكيرسيتي بتاعت ووتر، صح؟
في سكيرسيتي لانه
لبنان من
ما في
الدول
ووتر مانجمنت. هلا في مناطق ما فيها امطار كثير، وفي مناطق فيها كثير امطار وفيها كثير مياه بس ما في ووتر مانجمنت، فبالصيفيه بيصير في نقص وحاجه للماء.
هي من الدول يعني خلينا من الدول المحسوبة إنها عندها سكيرسيتي، لبنان والأردن وفلسطين. فهنا إدارة المياه مهمة، يعني واحدة من اختبارات التربة الزراعية الجزئية بتاعت المياه دي. على العموم انتوا أخذتوا فكرة كويسة اليوم يعني عن رغم إنها بتكون ممكن تكون هنا شوية يعني ما البراكتس المتعودين عليها، لكن أو ما الميجرمنت المتعودين عليها، لكن على الأقل زي ما بيقولوا we shed a light